On the 25th of May 2021, a switching operation was taking place at the Callide Power Station. During a planned step in the process, there was an unexpected loss of power to the systems critical for the safe operation of the turbine generator. In the switch room, the lights went out. In the control room, the screens went black. Within 2 seconds, this unit had gone from normal operation to something entirely different. And with no screens, the operators had no way to determine what had gone wrong. Over the next 34 minutes, despite the operators' best efforts to understand and regain control of the system, the turbine generator ultimately tore itself apart. This is how it happened. The Callide Power Station is located near Biloela, Queensland. The site has 2 coal-fired power stations, Callide B, with generator units B1 and B2, and Callide C, with generator units C3 and C4. C3 and C4 are adjacent and share a common control room. Stations B and C are separate and independent from one another. It was unit C4 where the incident occurred. In a coal-fired power station, incoming coal is burned in a boiler, heating water and creating steam, which drives a turbine. This spins a generator rotor at 3,000 revolutions per minute to generate electricity. This electricity is stepped up through a transformer and is exported to the Calvale substation. The substation is operated by Powerlink and is part of the Queensland power grid. The safe operation of Unit C4 relies on 2 key electrical systems, the AC system and the DC system. The AC system powers key equipment required for the operation of the turbine generator, whereas the DC system provides monitoring, control and protection, as well as backup functionality in the event of a loss of AC power. The AC system is connected to the grid and supplies large equipment. It powers the hydraulics that open and close the steam valves, which regulate the flow of steam to the turbines. It powers the pumps that provide lubrication oil to the bearings, allowing the rotor to spin freely without metal-on-metal contact. And it also powers the pumps that create an oil pressure seal, preventing the hydrogen gas that cools the generator from escaping. Meanwhile, the DC system runs a range of control and monitoring systems critical for the safe operation of Unit C4. In simple terms, it powers the brain and life support system of the unit. The DC system runs the unit protection, which monitors the turbine generator for issues and takes appropriate action in response. The DC system also provides power to emergency backup systems. For example, it supplies emergency lubrication oil and seal oil pumps in the event of a loss of AC. This system is primarily powered by a battery charger, which also keeps a battery fully charged. This battery provides important redundancy. If ever there was a loss of AC power, which would result in the charger ceasing to operate, the battery could continue to power the DC system. The DC therefore would still monitor, control and protect the unit, and its backup pumps would continue to supply lubrication oil and seal oil to the turbine generator. Unit C3 has its own identical but separate electrical system. There is a third electrical system called Station. Station AC provides supply for plant common to Unit C3 and C4, while Station DC primarily provides redundancy to both units. Station DC has its own battery charger and battery, while Station AC receives its power from the units. In the 18 months leading up to the Callide incident, an upgrade program had been initiated to replace the battery chargers at C3, Station, and C4. The C3 and Station battery chargers were replaced and successfully brought back into service. By May of 2021, the C4 battery and battery charger had been disconnected, and the battery charger had been replaced. During this time, the C4 DC system was configured to receive power from Station through a switch called an interconnector. Now, the battery charger and battery were ready to be reconnected to C4. The planned switching sequence had 5 key steps. Firstly, the battery charger would be connected directly to the battery to restore it to a full state of charge. Once the battery was charged, the battery charger would be disconnected. It would then be connected to the C4 system. Then the interconnector from station would be opened, disconnecting station and C4. Finally, the C4 battery would be reconnected. These steps would restore the system to its typical configuration. The plant has physical safety measures specifically designed to prevent 2 batteries from being connected to the same system. This means station must be decoupled from C4 before the battery is reconnected. But this sequence does require that the C4 battery charger be the sole source of supply in between these 2 steps. By 1:32 p.m. on the day of the incident, the first 3 steps of the switching sequence had been carried out successfully. The battery had been fully charged, the battery charger had been disconnected from the battery. It had then been connected to the DC system. At this point in time, the turbine generator was still spinning at 3000 RPM and exporting power to the grid. Then, as the 4th step was completed and the interconnector was opened, all of this changed. The opening of the interconnector initiated an almost instantaneous loss of DC power and AC power to the unit. Without power, the turbine generator had lost critical primary and emergency lube oil and seal oil pumps, but it was still connected to the grid. Without protection, the unit could not be disconnected, nor could it be shut down safely. And without power to their screens, the operators in the control room had no visibility or control of Unit C4, and no way of telling that the plant was on a trajectory towards catastrophic failure. But what had actually happened when the interconnector was opened? How did this lead to the loss of DC? And why was the AC system lost as well? First, let's look at the voltage level in the C4 DC system. Up until the interconnector was opened, this voltage was being supplied from station. A voltage level of between 190 and 242 volts is required for the system to operate as designed. So, when the interconnector was opened, the system required the C4 battery charger to maintain the voltage at this level. This did not occur. When the interconnector was opened, the voltage in the DC system instantly collapsed. To understand why, let's look at how the C4 and station battery chargers behave when they're connected to the same system. Before being connected, each battery charger maintains the voltage level in its respective DC system. This level is determined by each battery charger's configured output voltage. But when they are connected together, it's only the charger with the higher output voltage that supplies the system, lifting the voltage to this level. Meanwhile, the lower output charger detects that the voltage level in the system has increased and responds by decreasing its own output. Since the higher output charger continues to maintain the system voltage at this higher level, the voltage inside the lower output charger continues to decay. This is precisely what happened in the C4 charger. In the 74 seconds between the 2 chargers being connected to the same system and the interconnector being opened, the voltage in the C4 charger had decayed to nearly half of what was required. So the instant the interconnector was opened, the voltage in the C4 DC system collapsed to the level of the C4 charger's internal voltage, just 120 volts. And it was the specific nature of this collapse that led to the loss of AC power as well. But in order to understand how this happened, we need to look at how a mechanism designed to protect the AC system inadvertently led to its loss. A major hazard with high-voltage electrical systems is the occurrence of an electrical arc flash, an explosion caused by electricity passing through the air. When this occurs, it is critical to shut down the power source to prevent continued arcing and further damage to equipment. The system used to protect against arcing in Unit C4's high-voltage AC cabinets is called arc flap protection. The arc flap protection works by applying a DC voltage to a switch at the top of the cabinet. The presence of this voltage is monitored by a protection relay. If an arc occurs in the cabinet, the explosive pressure will blow open a flap on the top. When the flap opens, it opens the switch, collapsing the DC voltage to the relay. When the protection relay detects a voltage collapse below 164 volts, it determines that the arc flaps must have opened and then sends a signal to the circuit breakers to trip the AC power. On the day of the incident, however, no such arc occurred. Instead, because the voltage in the DC system collapsed, the protection relay incorrectly determined that an arc had occurred and the switch had opened. It then sent a signal to the circuit breakers to trip the AC supply. These circuit breakers are powered by the DC system, and in order to trip successfully, they need to be supplied with at least 101 volts. This is how the specific nature of the DC collapse led to the loss of AC. Because the DC voltage had collapsed below 164 volts, the protection relay interpreted that an arc had occurred and sent the trip signal to the circuit breakers, which tripped the AC supply to the unit, all before the voltage had decayed below 101 volts. If the voltage had remained above 164 volts, the protection relay would not have determined that an arc had occurred, and it would never have initiated a trip of the AC. If it had collapsed below 101 volts, there would not have been sufficient voltage for the breakers to operate. If it had collapsed below 80 volts, the protection relay would have powered down before it could initiate the trip. But the decaying DC voltage was at just the right level to misidentify an arc and to trip the AC power. Had the AC power not tripped, the battery charger would have recovered and restored the system voltage to the required level. However, without AC power, the voltage inside the battery charger decayed to zero, leading to a complete loss of the DC system. Within 2 seconds of opening the interconnector, both the AC and DC power systems to Unit C4 had been lost. When AC supply is lost, there's an emergency diesel generator that starts automatically and restores power to the station and unit AC emergency boards. But the loss of DC supply also managed to circumvent this backup system. When the emergency diesel generator detected that power had been lost, it automatically powered on. The station DC system then configured the station AC switches so that the station emergency board was being supplied by the diesel generator. However, without C4 DC power, the C4 AC switches could not be configured, preventing the generator from restoring power to the C4 AC emergency board. So, not only did the loss of DC directly cause the loss of AC, it also prevented any automatic recovery. There is also a mechanism in the C4 DC system that automatically responds to a loss of supply. This is called the Automatic Changeover Switch, or ACS. The ACS sits between the main board and distribution board and monitors the DC voltage in the main board. If this voltage falls below the required level, the ACS automatically changes over to supply the distribution board from station. However, the automatic switching capability of the C4 ACS had been damaged in a previous incident, and it could only be operated manually. In this state, the ACS had no way to automatically reroute power from station to the C4 distribution board. So seconds ago, Unit C4 was functioning normally. Steam was driving the turbine, spinning the generator at 3000 RPM and exporting electricity to the grid. But the sudden loss of both the AC and DC systems would lead to the destruction of the unit over the next 34 minutes. As soon as AC power is lost, the steam valves slam shut. But this loss of driving power from the steam doesn't result in the turbine generator slowing down significantly. Instead, because it is still connected to the grid, the unit changes from exporting power to importing power. And as it continues to spin, with its field switch open, the generator is now an asynchronous electric motor. And the unit protections that would normally prevent this by disconnecting the unit from the grid and safely shutting it down are unavailable due to the loss of DC. This motoring of the generator will continue for the next 34 minutes. Without AC power, the bearing lubrication oil pumps and hydrogen seal oil pumps stop working. And without DC power, the emergency DC pumps don't work either. Without all these pumps, the oil pressures in the bearings drop and the shaft begins grinding metal on metal and producing heat. And without seal oil pressure, hydrogen gas begins escaping from the generator and combusting in the air. On top of this, the loss of AC power means that none of the cooling systems critical for the safe operation of the turbine generator and generator transformer are available. These begin to heat up. Over in the control room, the C4 displays go blank because of the loss of power, and the operators are immediately bombarded by control system alarms. They can hear violent crashes and bangs coming from the plant. Something is seriously wrong with C4. Within minutes, the decision is made to evacuate the site, while some operators will stay behind to try and understand what's taking place on Unit C4. Has the boiler tripped? Is steam still driving the turbine? Are they still connected to the grid? But with the screens blank, they have no visibility of what is actually taking place in Unit C4. 10 minutes later, at 1:43 p.m, the generator hydrogen has completely leaked out and the fires at the generator have stopped. But the unit is drawing 50 megawatts and 350 megavars from the grid and continues motoring. Because the white metal layer of the bearings has completely melted away, the shaft begins to lose its center. Ongoing grinding generates immense heat. At this stage, the shaft has reached at least 730 degrees Celsius. 20 minutes later, the operators managed to restore their displays using another power source. But it's clear to the operators that the incoming data is inconsistent and can't be relied upon to make a safe and informed decision. Their major concern is avoiding an overspeed event. If they decide to ask PowerLink to disconnect the unit from the grid at Calvale, while it's still being driven by incoming steam, it will rapidly accelerate and tear itself apart in a matter of seconds. The operators ask PowerLink to stand by as they continue to try and make sense of the situation. It is at this point that the event enters its final stage. At 2:06 p.m, the excessive wear on the shaft causes the turbine blades to catch on the casing, and the shaft tears itself apart at 9 locations, ejecting chunks of shaft from the generator unit. A piece weighing more than 2,000 kilograms is thrown 5 meters across the ground like a spinning top. The barring gear weighing 300 kilograms is launched 20 meters into the air, punching through the turbine hall roof. With the generator still connected to the grid, large electrical arcs start to form, vaporizing the copper conductors, causing it to pull a massive 300 megawatts and over 1,400 megavars from the grid, nearly 3 times its rated export power. After 40 seconds of this, the arcing causes an electrical fault which is detected at the Calvale substation, leading to its protection systems operating automatically, finally disconnecting Unit C4 from the grid. By this stage, the generator and generator transformer are destroyed. The remaining people on site are then evacuated with no loss of life. But the incident destabilizes the grid, initiating a cascading failure that trips 9 major generator units across multiple power stations in Queensland. A number of factors led to the incident at Unit C4. When the interconnector was opened, the battery charger did not maintain the voltage in the DC system, despite the switching sequence requiring it to do so. Because the battery charger was the sole source of DC power at the time, this led to a voltage collapse in the DC system. And this voltage collapse incorrectly triggered arc flap protection, which tripped the AC system. Then, without AC power, the battery charger did not recover, leading to the complete loss of DC. Because the automatic changeover switch was unable to function in automatic mode, DC supply could not be rerouted to C4. This loss of DC meant the unit couldn't be disconnected from the grid and would motor for the next 34 minutes. It also prevented the AC system from being reconfigured to receive power from the emergency diesel generator. Operators had no visibility of the unit and were bombarded with more than 15,000 alarms. With no way to safely regain control of the unit, at 2:07 p.m, the incident reached its conclusion.